Hello everyone, and we are going to go through electric potential, also known as voltage, and this is the very first activity, 3.0. So you have the book, and what I want you to do is start reading Coletta, chapter 18, on voltage. If you are in Physics 131, you could also read chapter 7 in the Open University Physics OpenStax. If you have the night textbook, chapter 28 is what we're going to be going through today. If you're in 112, do the College Physics OpenStax chapter 7. But basically, everybody has access to this Coletta chapter 18. It's a pretty good book. It's not bad. This is going to be related to the sapling homework in 112, homework 4. In 131, homework 5, and there is a lab associated with this. It's lab 4 on voltage. So let's begin. You've probably heard of electric potential, but more in the term of voltage. They are the same things, okay? The term electric potential is analogous to the electric field. So we'll get into how it comes about and what it is in a second. But you've associated voltage with batteries, and it's also associated with lightning. And what we're going to find out later on is that we can view electric potential or voltage as almost like a height. And it's analogous to a height. And anyways, and then we're going to do some capacitors using voltage in the next chapter in circuits. All right. So what are you going to learn? Well, you're going to learn the term volt. It is the unit, SI unit for electric potential. You're also going to learn that it's calculated by a potential difference between 2 points. And that these potential differences of charge distributions can be created by integrating over a bunch of point charges. You're going to learn the concept of equipotential lines and also how charges distribute themselves in a conductor. All right. Voltage is also 1 joule per coulomb. Okay. So it's basically an electric field. It's not an electric field. A potential energy due to electricity per unit charge. Okay. But I want to point out that a volt is not a unit of energy. So it's a joule is a unit of energy, and a volt is a joule per coulomb. Okay. So you've also may have heard the term electron volt, and basically, in 1 electron volt is 1 joule. It's 1 joule divided by an electron. An electron's coulomb. So 1.6 times 10 to the negative 19th joules. All right. Some things that you've associated with it, we talked about a battery, flashlight batteries, 1.5 volts, a car battery is 12 volts. So basically, what is this that we've been referring to this entire time in relation to batteries? And how do we associate it with what we've learned with electric fields, energy, and also a Coulomb force. So we're going to try to relate everything to what is a volt, and how is it related to energy, and how is it related to the electric field. Okay? Well, suffice it to say, basically, electric potential or voltage is basically, it's the integral of the electric field in relationship to a distance, okay? So the electric field due to a single point charge is kq over r squared. When we integrate that, you get kq over r, all right? we know that the electric field is KQ over R squared. So basically KQ of voltage due to a point charge is KQ over R. But if we have the electric field, which is KQ over R squared, if you multiply that by R, then you have the voltage. So that's how this comes about. It's important to note that when you get at a very far distance away from R, so as R increases, the voltage will decrease. Okay. As Q increases, the voltage will increase. So V and Q are directly proportional to each other, but R is inversely proportional to the voltage. Okay. So I talked about earlier about how you could view voltage in a lot of different ways, and I want to emphasize that voltage is another way of looking at the electric field, and it's almost like it's actually like saying this: the electric field is to force as voltage is to energy. All right. So voltage is another interpretation of the electric field, and since we've integrated that electric field, what we find is that you can view this voltage as a scalar. It has no vector quantities to it. So what we've learned is that if something's a scalar, you can just view it as a magnitude, right? And in this case, we're going to view voltage as almost like a height, okay? So in a way, if you have a positive charge, well, that positive charge is going to create a positive electric field, which is going to create a positive voltage. And that is like looking at it as if a positive charge creates a mountain. Conversely, if you have an electron, okay, an electron creates a negative electric field, which in turn creates a negative voltage, and that would be like having a trough under sea level, or kind of like a valley under the sea level. Okay. So what is the relationship of the electric field to voltage beyond just the quantification? Okay. So here we have a metal object. We have a conductor, and it's got a bunch of positives built up along its surface. Well, what we had learned in the electric fields chapter is that the electric field is perpendicular to the surface of the object at any point. Okay, so right here, this is the surface, and notice that the electric field line is perpendicular. And since it's a straight surface, the electric field is going to be evenly spaced. But then when the surface starts to curve, the electric field will get bunched up, or it'll start to diverge, okay, as in this case. So here we have the electric field lines. Well, what is the relationship of voltage to the electric field lines? Well, here's the same object, and you can see the electric field lines, okay, and those are created from positives. Well, voltage lines are perpendicular to the electric field lines, okay? They're parallel to the conducting surface, so it's almost like you drop this triangular-like object into the water and you see ripples come out. And these would be the equipotential surface lines. Okay, so that's an equipotential surface lines, and notice that they start to, so you have almost like a ripple effect. And what you'll notice later on is that these equipotential lines get weaker and weaker and weaker the further out, because the voltage is dropping off, because the further out you are, the distance is going to increase, which is then going to drop down the voltage. So what we'll find out when we're looking at circular objects is that we're going to find out that the electric field lines are not equally spaced here, that we learned in the last chapter, and we're going to find out that the voltage lines will also not be equally spaced. So we'll find out that so if we look back at the equation, if the electric field goes up, the voltage is going to go up. Well, what that means here is if the electric field lines are close together, well, the voltage lines will be closer together too. So we're going to talk about how density of the electric field lines is analogous to density of the voltage lines. Okay, So here we have a circular object, so it's just a positive sphere. And notice that the electric field lines are kind of dropping off. It looks a little bit like a spider. So the electric fields are leaving the surface perpendicular to the surface and then falling to the ground. Well, the electric potential or voltage lines are perpendicular to these. So imagine just a little perpendicular right there. Okay, so if I go to draw this, I'm going to put on comments again. So I just went over here to the comments tool in Acrobat Reader, and when I hit that, this popped out and a bar popped out. Okay, and this bar has the ability we could input in a text field, we could draw, we could erase. So I could do a little drawing right here. I could erase that drawing, any part of that drawing. Or if I just click on it, you can just delete the entire that entire thing from the document. Also, I could put shapes with arrows, right? So I'm just going to point out that this is little perpendiculars at every little point. Little perpendiculars everywhere. Notice these are little perpendiculars. Okay. Notice also that right here, for example, here we have the electric field lines going out from some object right here, causing that. And so this voltage is going to be higher up. So since the electric field lines are leaving this area, we know there's a positive charge here because the electric field line is pointed away from a positive charge. And so that means this voltage, which is a height, is going to be higher up, and then it gets a little bit lower and a little bit lower and a little bit lower, right? There must be another object here, probably a negative charge, that is causing the lines to go into it and bend back into it, right? But notice that the density of the electric field lines here is greater than the density of the electric field lines here. If I drew that shape and I drew approximately same size shape right here, I was able to capture two electric field lines. Well, here is only one electric field line. So electric potential surfaces and electric fields are really different interpretations of the same thing. Okay. Voltage is a energy interpretation. Electric field is analogous to a force interpretation. Okay. So want to talk a little bit more about different shaped objects. So here we have a circular object and it's positive, so the electric field is pointed away. Notice that when the electric field lines are closer together right here, that also the voltages are closer together. Oops. So notice that the voltage lines are closer together. And as the electric field lines start to diverge, the voltage lines, the space in between the voltage lines, start to disappear. But here's something that's interesting. If you've ever looked at a topographic map, the difference between the height lines is always going to be the same. So what you'll notice, if you have a map, there may be 100 feet difference between one height line and another height line. Well, here, there seems to be, this is 30 volts right here. And over here, we have, this is 30 volts right there. And right over here, it looks like we have 20 volts. 50 volts. So what does that say? That says that this is 50 volts, this is 30 volts. That means there's a 20 volt difference between these two lines. Well, let's go to the third line in. Well, that's 70 volts, and this is 50 volts. So there seems to be a consistent change in voltage between the voltage lines, the equipotential lines. And so, since we know that now, this is 30, this is 50, this is 70. This has to be 90, and then this innermost line has to be 110. Okay? So we could actually use that delta voltage difference to actually count what the highest voltage is. Okay. And also notice that even though the lines are getting closer together, they're still maintaining, so these two equipotential lines are very close together. Turn it. These two equipotential lines are really close together, yet these two equipotential lines are really far apart right here. So even though they're far apart, that means but the voltage difference is the same. This is 20 volts difference. This is 20 volts difference. Okay. On another type of object, this is a capacitor, and we've looked at capacitors before. This, you have a line of positive charge, you'll have a line of negative charge, and you'll have a very homogeneous electric field, a constant electric field. That means since the electric field lines are equally spaced, the voltage lines will be equally spaced. Okay, because the surface is not curving or anything like that. Okay, so that means here you have the highest voltage, which is 20 volts. This is 0 volts, and then negative 20 volts. As we get closer to the negative plate, you get closer and closer to you drop down in voltage. Okay, but again, notice this symmetry between electric field and voltage. If the electric field lines are equally spaced, the voltage lines will be equally spaced. All right. Well, you could have two objects in relationship to each other that are producing their own voltages and electric fields. Well, when you get them close enough to each other, well, these electric field lines are going to start joining together. And sometimes their voltage lines could be interpreted as being joined together. Okay, so this is not two spiders giving each other hugs. This is an electron and a proton, and the electric field lines are leaving the proton and coming in towards the electron. Okay, well, the voltage lines are going to be very askew as well. Okay, so on this side of this is now going to be a 0 volts in between the two objects. Okay, and notice that on the right hand side of this, since this is a positive, it will be positive, and then it'll drop off to 0. On the left hand side, this will be a negative voltage area, and the electron will have its highest voltage. Will have it actually, I'm sorry, its lowest voltage close to the electron, and then drop off to 0 further away. When you have two protons close together, their voltages add up, and they actually, you have like charges, their voltage will actually add up. And so even though the voltage here is dropping off due to this proton, it's also dropping off here, and then they kind of add up. So if you have two like charges, you'll actually have to find the voltage here at this difference here, and then just add it to the other one. And since they're scalars, not vectors, you don't have to worry about directions of those. They'll just be high voltage or low voltage or just magnitudes, okay? And I want to point out in the equation here, notice that there are no absolute values. Well, what that means is that the charge does matter. So here, before, we would put an absolute value around the charge when we're talking about an electric field. Well, since we're dealing with a scalar, that charge is actually going to matter. It's what gives it a positive voltage, and not the direction of the electric field. Okay? Well, let's map out. I talked a little bit earlier about mapping out what something looks like. So we know, I showed you earlier that if you have a proton, it will create kind of a mountain or a high positive voltage. And that's looking at it in 3 dimensions. Well, we're going to make 2-dimensional drawings now, interpretations of these voltages and electric potentials. Okay, so in this one problem right here, we're going to just look at this one right now. You have a positive object, and it's going to be placed about right here. I don't know why it keeps doing that. Okay, so you have a positive, you have a little proton that's placed right here. Okay, so that's the center of the proton. And so a positive voltage is going to create a high positive value. So this proton is going to have its highest point right here. And since distance is inversely proportional to voltage, the further out you go, the more it's going to drop off. So right here is the first voltage line. It's going to be dropped right here. So it's going to then drop off. And the next voltage line is going to be here. Sorry, I'm trying to be consistent with this. It should be right here. The next voltage line is going to be right here. But here's the interesting part. This other voltage line is going to be way out here, further away. So what you see is a gradual dropping off. And eventually it'll drop off to 0. It won't go below 0, okay, because you would have to have a negative voltage, and the only way you get negative voltages is with an electron. Well, on the right-hand side, you're going to have the same type of thing. You're going to have it gradually dropping off on the right-hand side. So what you get is something kind of looks like, almost like a volcano. You're talking about positive charge. Right? So this right here, horribly drawn, is supposed to look similar to this, where a proton, you have a proton right here, and the voltage is dropping off the further away you get, because voltage and distance are inversely proportional to each other. Okay? Well, what does the voltage look like due to a proton and electron being close to each other? Well, we saw earlier that at the center, the voltage is 0. If you have a negative voltage here and a positive voltage here, they're going to overlap and add up to be 0. So we know this is going to be the 0 mark. And we know the proton is going to be about right here. So here's where we're placing our proton. And we're looking at this from the side. This is a top-down view. This is a side view. The electron is right here. Well, let's map out the proton. The proton's got a first equipotential line, oh boy, which is about right here. And then it's going to drop off a little bit more. Basically, it's going to look like that as it drops off. And on the right-hand side, it's going to take longer to drop out because there's nothing making it drop down faster. So this side is almost reflective of what is going on this side here. So on the right-hand side of the proton, well, now the electron is creating a negative voltage right here, which now is going to do this. So this kind of looks like an S. All right. And then the negative, the electron, is then going up to 0 and dropping off in the same shape that this is dropped off, but almost like a mirror image. So that's what a proton would look like. And this is what the electron part would look like. Okay. Over here, we had seen this shape before with the capacitor. And we notice at the center of the capacitor, you've got a 0 voltage because it's a halfway point in between the positive plate and the negative plate. So we know this is here. And since this is very ordered, the high voltage is here, the low voltage is here. Since the electric field lines are evenly spaced, the voltage lines are going to be evenly spaced, so you're going to have a constant dropping off in voltage. It'll be a straight line. Pretty cool, huh? So using this interpretation of voltage as a height or a valley underneath water level, this would be water level, 0 voltage. Water level, 0 voltage. This is dropping off to the sea. And doing almost using topological maps as to help us interpret what voltage really is. And so since voltage is now kind of interpreted as a height, well, when you raise an object up off the ground, you give it potential energy due to gravity, and then you let it go and it turns back into kinetic energy. Well, that's what we're going to use voltage for too. You raise a proton up in here, and it's going to fall down. It's going to actually, that positive proton right here, you put a positive proton here, it'll be pushed to the right towards the electron. Okay? So this is what a topological map looks like. And then we have a mountain right here. Okay? So this part of the mountain is this peak right here. And so this is looking down on the mountain, okay, and this is looking from the side. So it's almost the reverse of what we just did. This is looking down on top of the object, and this is the side. Well, here we have the side, and here's looking down. So in a topo map, things are divided up in the height by feet, and you could tell me right now what the change in voltage is between each line. So what's the change in voltage between right here, between this point right here, and this point right here? Well, this is 400 feet, and this is 350 feet. So this looks like a difference of about 30, this difference. Let me change that. Is going to be a difference of 30, right? Well, if this is a difference of 30, and that means now that every height line, okay, is also a difference of, oh, I'm sorry, that I said 30, and that should be 50. It should be a difference of 50 feet, okay? Because 400 feet minus 350 feet is not 30, it's 50. Anyways, good job, Jim. Good job. Can't subtract. Here we go. Well, notice that these two height lines are really far apart, okay? Well, this is going to be 300 feet, so 300 feet. I'm just tracing the line over here. And this line is 250 feet. So even though this difference is really far apart, okay, so this difference is really far apart right here, well, that is still just a difference of 50 feet. Okay. And that's analogous to saying this right here, from here to here is about 50 feet height difference. Okay. Draw this right here. So from this point to this point is 50 feet. Well, that means shoot, sorry. Let me get rid of that and redraw that again. So this difference right here, so we said this height right here is 250 feet. Well, this part is going to be 50 feet here. So this is going to be a 50-foot difference. Well, that means this is also going to be a 50-foot difference in height. So that's what these lines are. They're little chunks of this mountain up by 50 feet. And then you have another 50-foot difference here, and then another 50-foot difference, and then another 50-foot difference, and so on and so forth. So you're just taking little slices of this mountain. Well, that's what we're doing here in a three-dimensional term. So that's what voltage is. I view it as a height, and that's electric potential is voltage. So that's what you were supposed to learn from this. And so point charges wise, you have a positive point, you have a positive guy that creates a mountain, okay? And we have an electron that creates a trough underwater, okay? So if this is zero potential right here at its base, then this is going to be a very high potential here, okay? And this is zero here. Well, here, this is 0 volts, and this is a negative voltage. So put a little 0 volts, and this is a negative voltage down there. So this is sea level here, and then we're going further down underwater. Here, this is 0 volts, and this is a positive voltage right here. So you could see that this charge here, the reason why this charge is what is creating that height. And that's why we need to keep the sign in there and not put absolute values around that. Okay. So that is the relationship between electric fields and voltage. They're interpretations of the same thing from different perspectives, from a utility term, from a utility perspective. Well, let's do an exercise. I want you to take a look at this. Okay, right here. 1, 2, 3, 4, 5, and 6. And here it is relationship to this mountainside. I want to see if you could look at this picture and then map out 1, 2, 3, 4, 5, and 6. All right? So go ahead and do that now. Notice that the 0 voltage mark is right here. And suppose you were walking from 1 to 2, 2 to 3, to 4, to 5, to 6. What would it look like? So here's the path that you're walking. You're walking this path. How would it look like as you walked? How would the height look like and change, the elevation change as you went hiking, following that path? All right? Go ahead and take a moment and pause the video and try this. Okay, here we go. So so here we go. I'm gonna go ahead and try this. It says it starts off at number 1, and if I follow this number 1 line all the way around, it looks like that is 40 volts. So I'm gonna go ahead and put a little dot at 40 volts because that's where number 1 is. Okay, and the next equipotential line is this one right here, and that, when I follow it around, is 60. So that means in between the voltage difference, 60 minus 40 is 20. So that means there is a 20 volt difference in between each line, and I'm going to use that to count what number 2 is at. So that's 60. That means this has to be 80. So 80 right there. This next one is going to be 100, and it looks like about 120. So number 2 is going to be, so this is 100, and this is going to be 120. So this is 100 volts, and this is 120 volts. So that means number 2 is way up here. Okay, so I've walked from 1 to 2, and since these voltage lines are not equally spaced, it's not going to be a straight line. It's going to be kind of a curve. Okay, now I'm going to go to 3. When I walk to 3, well, I'm walking back down from 120 volts all the way to this voltage line, which is the same voltage line as number 1, which we found was to be 40 volts. So now this is going to curve down because, again, the voltage lines. So I'm going to make it look as curvy as I can. Okay. And now that we're at 3. Well, we're going to have to walk up to 4 because there's a proton here. So 60 volts, 180 volts, 60 volts, 80 volts. It looks like it's only going, 4 is only going up to, it might be going up to 120. It looks really close. It's hard for me to see, but I'm going to guess it's going back to 120. So that means I'm curving back up to 120 volts at right here. So 3 to 4 is going back up to the same height. Okay. Now walking to 5. Walking to 5, they say 5 looks like it's right on the 120 volt line. So 5 is going to happen right about here. And again, it's got a curve because these lines aren't equally spaced. So it looks like it's dropping quite rapidly. And then here we go to 6. Well, 20, this is negative 20. This looks like this next line might be negative 40. So I'm going to just guess that 6 is way down here. And when we get to 5, well, this next one, if that voltage difference is 20 volts in between each one of these lines, then this has to be 0, right? And it is. So that means the 0 point is about right here. So it's going to continue to curve down, and then it's going to start curving the other way after the 0 mark. So this should be more of a smooth drop. And then it's going to drop down. Kind of looks like a kitty cat. Anywho, this is the interpretation if you walked this path. And you can kind of see, if you were looking from this direction, that it would kind of look a little bit like a peak. And then to go from 4 to 3 to 5 to 6, now you're kind of looking in this direction at this mountainside. So, well, that's how to interpret voltage lines as heights. All right, let's go ahead and do a problem. Let's rank these voltages from highest point to lowest point using this electric field that looks like it's kind of warped. So what would be the smallest voltage and what would be the highest voltage? And then what we're going to do is also look at ranking the electric field from being strongest to weakest. All right, so we had talked about this before. So let's go ahead and rank the voltages from largest to smallest. Okay, so go ahead and pause the video and take a moment and try to figure out what the voltages are. Which one's higher? Is A less than B? Is B equal to C? What do you think that is? Go ahead and pause the video and try that. All right, we're back. Well, let's take a look at this. For me to figure this out, I have to kind of look at what might be causing this electric field. And so the electric field is pointed to the right, and it's kind of bending out and away. Well, that tells me that there must be a positive object over here causing this. Okay, so there's probably a positive object causing this electric field. Okay, and that this proton, or this positive electric field, see, if it started bending back in upon itself, well, then that would tell me that there's a negative over here, but there's not. So there's no negative over here. So this is just being caused by probably one or a couple protons here. Well, if that's true, then that means this voltage line right here is closest to the proton, and since distance is inversely proportional to voltage, the closer I am, the higher the voltage. And then it's going to kind of drop off a little bit, and it's going to get a lot more spaced, and then a lot more spaced. So if I were to actually interpret the voltages dropping off, the voltages would be really close together, because notice the electric field lines are getting further apart. That means the voltage lines have to be getting further apart. And then what we have is they're getting much further apart. So it looks like A, the voltage at A, is going to be the highest. And then the further away you get, the voltage at B is going to be not as high as A, but the second greatest. And then it looks like the voltage at C is less than the voltage at B. And then finally, the voltage at D is way out here, which is going to be the weakest of all the indicated points. All right. Okay. Well, how do we figure out, I hope this was informative for you, this part. Let's go on to ranking the strongest electric field to the weakest electric field. Well, the same interpretation, a similar interpretation can be made with the electric field. If you recall, the electric field equation is, all right, there we go. The electric field equation is, I don't know why it's putting a box around that. So this is supposed to be an E. Electric field is equal to KQ over R squared, absolute value, right? Well, what that means is that if distance increases, then that means the electric field is going to decrease. Okay, so the further I get away from the source of the electric field, the weaker the electric field is. Notice that the electric field lines are getting further apart. If I take a little slice here, I'm going to draw a line this big. Notice I get two lines right here. I'm going to draw the same distance line here. Notice I'm getting 3 lines there. Here, I'm going to draw the same distance line here. I'm getting 4 lines, electric field lines. And then here, draw the same distance line apart here. And I'm getting all 5 of these electric field lines. Well, that tells me that the closer you get to this object, the denser the electric field lines, but also the denser the voltage lines. And so what can be said is that the electric field at A is greater than the electric field at B, greater than the electric field at C, is greater than the electric field at D. So we're just going in terms of magnitudes of strengths. Okay, I want to just point that out. A positive and negative electric field can be interpreted as it is a vector, but we're just talking about the magnitude of the electric field, and it's going to have a higher number here than it is over here. Okay, so that's the relationship between electric field and voltage in quantitative terms. Well, a minor quantitative analysis. Okay, let's do another problem. I want you to take some time and try to perform each one of these tasks. And I should have done this in a easier order, but I want you to rank the voltages at each one of these points: voltage A, voltage B, voltage C, voltage D. I want you to rank the strength of the electric field line, and again, what I mean by that is the electric field is going to be, we're going to be talking about the magnitude of the electric field and not its direction. But I also want you to draw the electric field lines going through B, through A, through C, and through D using a vector. So please try all of these tasks on your own. And just keep in mind that the electric field lines are going to always be perpendicular to the voltage lines. And what we're looking at is voltage lines, equipotential lines. And I want you to go ahead and figure out what the voltage is at each one of these points and rank them from highest to lowest. Rank the strength of the electric field at each one of these points from strongest to weakest, and then draw electric field lines through each one of these points. Please do so now and pause the video. All right, let's go ahead and try this. I'm going to go ahead and start with the easiest of these tasks. So, that was weird. I'm going to go ahead and draw, we're going to rank the voltages, all right? So for me to do that, I have to kind of figure out what the voltage difference is. So for me to figure out what the voltage at A is, I could see that A and D are on the same voltage lines. I could see this is 0 volts, but this one isn't listed. Here, C is not listed. Oh, here we go. We have a negative 100 volts, and then there's a blank, and then 100 volts. So that tells me that if they're equally spaced, and we're going to probably be using whole numbers, that this is probably 50 volt differences. So 0, negative 50 volts, negative 100 volts, negative 150 volts, negative 200 volts, negative 250, and so on and so forth. So that tells me that this is sea level, and this is underwater. It's getting deeper and deeper underwater. And this is a mountain top of some type. And this is another mountain top of some type, probably over here. So that tells me that there's some source of positives over here. There's probably some source of positives over here. And there's probably, since these voltage lines are getting very close together, that means there's probably a collection of electrons over here. Well, let's start with A. So if this is negative 50, this is 0, that means this has to be positive 50 volts. Okay, and since A and D are on the same voltage line, that means D is going to be also positive 50 volts. Okay, then we're at 0, and that C is on the negative 50 volts line, and that B looks like it's on the negative 200 volts line. So the way this is looking like, it's looking like V sub A is equal to V sub D, and they're both positive 50 volts. Then it looks like C, so they're both equal to each other and greater than C, which is negative 50 volts, and then greater than B. Okay. All right, so those are the heights. Let's go ahead and try to rank the electric fields. Well, the electric field is not exactly equal to voltages. They're not equal to each other. In fact, voltage is equal to E dot R. Okay, so this is the relationship between the two. But what we could see here is that the voltage lines are really collected together here. So that means this is going to be a strong electric field here. And they seem to get further and further spaced apart. So that means if they're spaced apart, then the electric field is going to get weak. It's going to be weaker over here. Okay. And that C and D look like they might be the same thing. I need to actually measure this. So what I'm going to do is I'm actually going to draw little green lines. Actually use blue. And I'm going to draw the difference here. So this difference here, actually draw a little bit larger one. So by drawing this size of a line, blue, I'm going to draw this size of a line here too. It seems to be only 2, and this is the same size line. That is going to be D. So it looks like C and D might be the same thing. It's kind of hard to tell. B is definitely the strongest electric field. So I'm going to put that here. So E sub B is going to be greater than everything else. And it's looking like A, I drew that, A is going to be the weakest of all. So E sub A is going to be the weakest. And I'm guessing that E sub C is equal to E sub D. They look really close to being the same thing. You might think that D might be greater than C. It's too close for me to call that. But that's my interpretation. I could be wrong. Right? Well, let's go ahead and do the last task, and let's draw the electric field lines. I'm going to use red for the electric field lines. And draw that up there. So I'm going to draw the electric field lines. Now, electric field lines go from positive to negative. So we know the electric field lines are going to be traveling towards the collection of electrons. If this is protons right here, and this is a bunch of protons here, so there's a peak here, and there's a peak here, that means protons are causing those peaks. Okay? And that electrons are collected over here. Well, that means through B, the electric field has to be pointing in that direction. So if I continue that electric field line, I'm trying to draw the electric field lines to be perpendicular to the voltage lines at each point. And so it's going to go away from the positive and towards the negative. So there's a voltage line, electric field line through point B. Let's do the electric field lines through A. Well, it's going to be going from here, pointing away, towards the negative, to the lower voltage. It's going to continue going, continue going, continue going, continue going. And it's going to be pointed up and to the right. But here's where it gets interesting. It actually has to bend down and come in here. I don't know if it splits off and goes that direction, but it seems that whatever is over here is causing a higher voltage peak. If this is the highest it goes, this is only 100 volts. This has got to be, let me see, 150, 200 volts right there. So it's probably going to be bending this way. C's voltage is going to be perpendicular at each one of these points. And it's going to be pointed from high voltage to low voltage, or from positive to negative. But again, they're all going to be at 90-degree angles. And D is going to be doing the same thing. It's going to be kind of bending this way too. So there you go. That's a drawing of the electric field lines interpreted by the voltage lines. And you could then make some really cool presumptions about the strength of the electric field. Oops, I should have actually put magnitudes around those little electric field equations. Let me do that. And there you go. Let's keep moving on. So the best way, the only way to measure really what the electric field is actually with a change in voltage. Okay, you could get a voltage at one point. Okay, but what we're going to be doing is getting voltage differences and helping and using the voltage difference to interpret what the electric field is. All right. So you're going to have two different points in outer space, one point here and then another point here. Oops. And then we're going to be looking at the voltage difference. Now, here, since these things are scalars, it doesn't matter the path that you take. If you take path I, that's you have a voltage here, okay, and you have a voltage here. So the voltage lines would look like little rings, and this ring would be much further. Whoops. Much further out. Okay, so let me make this one a little bit better of a drawing. Let me go back to this. So, oops, click on that pencil. All right. So this guy is going to be doing this. So it's a horrible circle. But anyways, so if you have a voltage here, and oh, just real quick, which voltage would be higher, A or B? Well, you can see that which one is closer to the source is the one that's going to have the higher voltage, if it's a positive voltage source. So that means VB is greater than VA. So we answered the first question, which one has a higher voltage or electric potential? Which path is going to have a higher, which path, 1 or 2 is going to result in a larger voltage difference? Well, they're going to be the same thing. And I should have said which one's going to have a higher delta V here. Sorry about that. So which path is a higher voltage difference? Well, they're the same. Path doesn't make a difference. Doesn't mean if you took this path to get from here to here, yes, you would have moved a farther distance, but that doesn't matter. The voltage difference is what matters. If this is a higher voltage than here, and it doesn't matter which path, they both end and begin in the same way. All right, which is a clue on how we're going to use this information, because when we're talking about this type of stuff in energy in Physics 121, you had to use that interpretation as well. All right. So here's a task. What I want you to do is I want you to go ahead and interpret the delta voltages at, this is our old map that we did earlier, the voltage differences at A, B, AC, D, E, and F. And you're going to have to interpret the voltages of the equipotential lines. So I want you to try each one of these tasks and see what you come up with. Is it going to be a positive or negative voltage or a zero voltage? Okay, so I'm just looking for positives, negatives, or zeros here. And actually, you're going to give me a numerical answer too. So like a positive 20 volts, a negative 20 volts, or a zero voltage difference. Okay, so write these. You're going to have to interpret this in terms of numbers, the voltage at B and the voltage at A, and then give me a potential difference. So let's do this first one together, and then I'm going to let you try all the rest yourself. Okay, so the voltage at B. The voltage at B is on the 40 volt line. So I'm going to write 40 volts right here. Voltage at B is 40 volts. The voltage at A is 60 volts. So 40 volts minus 60 volts is going to be negative 20 volts. All right. So I want you to do that for every one of these tasks. So please pause the video and try this out yourself. All right, we're back. Let's try the voltage at A. The voltage at A is 60 volts. And the voltage at F is on 20 volts. So this is going to be 60 volts minus 20 volts, which is going to work out to be a positive 40 volt difference. All right. Cool. The voltage at F is going to be 20 volts. And the voltage at C is going to also be 20 volts. So 20 volts minus positive 20 volts is going to be 0 volts. Let's do the voltage at A and the voltage at E. The voltage at A is 60 volts. And the voltage at E is negative 20 volts. So this is going to be 60 minus a negative 20 volts, which is going to be a voltage difference of positive 80 volts. Okay, so it's that minus. This is the voltage difference, and you have a negative 20 volts, so it's actually going to add on to that. How about the voltage difference between B and C? The voltage at B is 40 volts. The voltage at C is 20 volts. So 40 volts minus 20 volts, a positive 20 volts, is going to result in a positive 20 volt difference. All right. There's just a really quick, easy task to practice getting voltage differences by looking at an equipotential topo map. Okay. All right, you have a lab tutorial that you're going to do in the next task. So let's get you started. So what you're going to do here is you have Q1 and Q2. All right, they're both positive Qs, but you'll notice some differences within them. So notice that all the points that are marked that you're going to do a task for are marked with lower cases for Q1, and then notice that Q2 is associated with uppercase letters. So here we have EA compared to E lowercase a and to E capital A there. So that means we're comparing the electric field here at this point to the electric field here at this point. But you have to be careful, okay? Because starting off this, you have to figure out which one is creating which one is got more charge on it. Well, does Q1 have more charge, equal amount of charge, or less charge than Q2? Well, what we learn with the electric field stuff is that the number of electric field lines is analogous to charge, right? So if E is equal to KQ over R squared, if Q goes up, then the electric field is going to go up, and that means you're going to have more electric field lines. Well, I'm going to count electric field lines, right? So when we did the flux chapter, the amount of electric field lines is essentially the charge. So I see 1, 2, 3, 4, 5, 6, 7, 8. 8 electric field lines here for Q1. Q2, it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it looks like Q2 has twice the electric field of Q1. Well, that makes Q2 larger than Q1. All right? Well, that is going to color how we view electric fields now. All right? So in order to figure out electric field line stuff, I'm gonna go ahead and erase this and redraw it so we just have the equation. Okay, and that's gonna help me. E is equal to KQ divided by R squared. That's an R. And that voltage over here is equal to KQ divided by R. And I should put the absolute value around this. Voltage, again, has no absolute value. All right. Well, if EA is right here, and so the electric field at A that's a distance r away, and so is the electric field to lowercase a, that's also a distance r away. So I have the same distances, so that's not going to cause a difference. But Q2 has twice the charge of Q1, which means the electric field here is going to be twice as strong. In fact, you could see that there's a higher density than this, right? The density here is weak. The density here is a lot more. Well, that's going to tell me that the electric field at capital A is going to be greater than the electric field at lowercase a. Cool. All right, in this next task, you're just going to be comparing the electric field at 2 points on one object, just the Q1 object. So compare the electric field at C to the electric field at B. So go ahead and do that now. And we're just talking about the electric field strengths. So there should be little absolute value lines around these guys. So I'll draw those here. And that's what I believe Dr. Summers at MCC was asking us to do. Compare the strengths of the electric fields. All right. Let's go ahead and compare the strength of the electric field at C to the electric field at B. Well, the electric field at C looks like it is 2r away. And I'm only going from the fact that he's saying that this is 3r away. And so that means this distance must be about 2r-ish. Guessing, not sure. But they look like they're equal distance from Q1. So what that tells me is that the electric field strength there is equal to the electric field strength at B. Okay? Since the electric field, since they're equidistant, that means and they're on the same charge, due to the same charge, the electric fields are going to be equal to each other. Compare the electric field, there we go. Compare the electric field at D to the electric field at C. So we have the electric field at D, which is 3r away, and C is about 2r away. So since our distance has gone up, distance goes up, it's inversely proportional to the electric field. Our electric field is going to decrease. That means D is going to be less than C. Oops, I circled the wrong one. Oop. It's getting worse. All right, here we go. The electric field at D is less than the electric field at C. All right, go ahead and try the voltages. We're going to compare the voltage at D to the voltage at C. Well, again, C is closer to the source, so that means the voltage is going to be greater C is going to be closer to the source than D. So that means this is going to be the case where the voltage at C is going to be more positive than the voltage at D. It's going to be a higher height. All right. Let's compare the voltage sub lowercase e to the voltage of capital E. So let's compare the voltage at E here to the voltage at E over here. Okay, at point E here. Well, they're the same distances away, right? But this has got twice the Q. So if Q goes up, then voltage is going to go up. So that means since they're the same distance, the voltage at E, capital E, is going to be greater than the voltage at lowercase e. All right. The last one, we're now doing a voltage difference part. What's the voltage difference between voltage difference D to E? Well, that's on the same voltage line. So this is going to be 0 volts. BC is also on the same line. So that voltage difference is going to be 0 volts. That means they're going to be equal. All right. So what I want you to do is I want you to try Equipotential electric fields handout right after this. Okay. And mark it up just like I did. You'll save it and then email it back to me. All right. So this will get you started. So I did the left side. You'll have to do the right side. Moving on. We're going to actually use what we just did to help us with these conceptual problems. Okay, so what we have is marks of points 1, 2, 3, and we have a positive charge there. Okay, and we're going to be doing the same thing, and you can see the answer is already indicated down here. Okay, but how is this true? So we're going to also use these equations here. So we're supposed to rank these from largest to smallest. Okay, well, 1 and 2 are both really close, so they're really close, so the distance is close, so the voltage is going to be high here, and they're the same distance from the source. So that means voltage 1 and voltage 2 are going to be equal to each other. 3 is further out, and so the voltage is going to drop off and approach 0 at some infinite distance away, right? Some infinite distance away. And what I mean is, if this blows up, whoops, Control Z, I'm getting all excited here. If this blows up to infinity, well, that means this is going to drop down to 0, right? So as this increases, this is going to decrease. So the further distance you get away from the source, eventually that voltage will become 0, right? And that's going to be the same thing that happens with the charge here over here. In this case, on the right-hand side, so voltage 3 is the weakest of that. Okay. So what we're going to do is we're going to go over here to this one. Now, this case, the negative Q1 is here. And again, voltage 1 and voltage 2 are on the same line, so that they're going to be equal. But they're closer to the lowest point. This is a negative source, so that means the voltage is going to be very negative here and very negative here. Okay? So that means the voltage at 1 and the voltage at 2 are both negative and the lowest. And then over here, voltage 3 is a further distance away. And again, as you go from, as distance increase, voltage is going to decrease. So way over here, the voltage is going to be 0. And then closer you get to this is the more negative the voltage. What that means is the closer you get, the more negative the voltage is. You're going down in height, so that's a lower height. So this is actually voltage 3. Even though it's negative, it's not as negative as V2 and V1. Okay, 3 is closer to the 0 voltage, which is actually higher up. So we're underwater here in this case, where voltage 0 is sea level. Let's interpret these different problems, okay? So this is like another worksheet that you're going to have to do later on, where you have to interpret voltages at different points. Well, you have a negative 2Q right here. You have a positive 1Q here. And what you're supposed to do is rank the voltages at different points. Well, if this was a negative 1Q, and this is a positive 1Q, you could call that voltage right in the center 0. So that's a clue in doing this. So I want you to pause the video and attempt this problem right here and try it out. Okay? So let's see you do this one. Pause the video now. All right, here we go. So here we have, let's try to find where, let's estimate where the 0 is. If this is a negative 1Q and this is a positive 1Q, the voltage right in the center line would be 0. But it's not. That means since this is much more deeper over here, and this is twice as deep as this is high, I'm imagining we're looking down on a mountain here and looking down on a trough underwater. I'm trying to find where sea level is, and I bet you sea level is going to be somewhere on this side. It's not going to be here in the middle. It's going to be a little bit there. So that's where the 0 voltage is. And that means to the right, this is going to be a positive voltage. 2 is probably a positive voltage, but it's definitely, okay, because you got this negative 2Q here, it's going to, even though it's equidistant that 3 is, this negative 2Q is dropping it down, to, dropping the voltage at 2. And then we have a high positive, and then it's going to, this is going to be a much more higher peak, okay? So it would look like dropping off to here, and this one is dropping off to 0, and then it's going further down underwater here. So notice that I'm drawing a little graph of voltage versus distance, okay? And that means this is 0 volts right here. This is a positive voltage here. And this is a negative voltage right here. So this is going to be really negative. And then it's going to go to approach 0. So this is a negative voltage here too. So basically the voltage at 1 is the weakest. The voltage at 2 is positive voltage, but not as positive as 3. All right. Why don't you go ahead and try the capacitor problem? Okay, and we've already kind of done this before, but go ahead and try it and see what you get. Pause the video now. So in this capacitor problem, again, I'm going to try to guess where the 0 voltage is. That's my strategy in trying to figure out what the voltage is. So in the capacitor problem, the very center of the capacitor is always 0 voltage. As long as an equal number of positives here, equal number of negatives over here, this is going to be 0 voltage in the center. And since 1 or 2 are right next to each other along the same vertical, they're both going to be the same voltage and positive. 3 and 4 are going to be negative and the same voltage. That means 1 is equal to 2. Voltage 1 is equal to voltage 2, but greater than voltage 3 and voltage 4. These are both negative and equal to each other. All right. Let's do the last problem. This is a lot like that one electric field problem that we did earlier. So go ahead and try this one out and pause the video and rank those, see if you could figure out why these voltages are the way they are. Okay? So go ahead and pause the video and try that. All right, here we go. Let's try to figure out what the source is. It's looking like the source here is going to be a negative Q right here. And so these are the electric field lines. Okay, electric field lines, and they're kind of curving into the source. It's going straight. Okay. And what that means is somewhere really far away from this negative Q, remember a negative Q is going to, the closer you are to it, the more negative it is. And when you start to get really far away, it starts to approach 0 volts. All right. So the distance is increasing, so that means the voltage is going to be dropping to 0. So that means somewhere way out here is 0 volts. And then the closer we get to the source, the more negative it is. So that means voltage at 3 is going to be a negative voltage, a very negative voltage. But 2 is going to be a little bit greater in voltage, because now we're going up in height. And the voltage at 1 is going to be even greater in voltage, but still negative. So all three of these voltages are greater. but voltage 1 is closer to 0, voltage 2, and then voltage 3. All right, so we've gone through all of the very first lecture on voltages. Okay, so please move on to the next activities and mark up your PDF docs, and make sure to save your name and send it back in to me when you're finished. Thank you.